So you already know polynomials, and we know y is equal to x in some way. And in some form or another, there can be numbers manipulating this. And we've seen this quite a bit. For example, y equals 3x minus 2. So whatever x is just a number. Multiply it by 3, take 2, you get y. Same with y equals x over 3 plus x squared. Same with y equals 6 lots of x cubed take x all squared. You can get as complex as you want with this, but we just have a y and an x being manipulated by numbers. But instead of putting x to a power, what if we use x as the power? So the power changes. We get y equals 3 to the x, take 2 instead. So whatever x is, you put 3 to that power, and then you take 2. Same with y is x over 3 plus 2 to the x, or y is 6 lots of 3 to the x, take x all to the power of x. We can still graph this obviously, because we only have one unknown, y. When we substitute x for any number, you just solve for it, but the graph will look substantially different. On the left is a typical polynomial, so a is just a random number, and in this case a is 2. X squared, y is x squared, so whatever x is, the horizontal line, y is going to be its square. On the right, y is equal to a to the power of x, where a is 2. So whatever x is, the horizontal line, y is going to be 2 to the power of that value. Exponentials usually are written in a general form, which is that y is equal to a lots of k to the power of b lots of x minus c plus d. And in this general form, a, b, c, and d do different functions. So a vertically dilates the graph, b horizontally dilates the graph, c translates the graph horizontally, and d translates the graph vertically. But it's all based on that original exponential graph that we had a look at. There's another thing called a logarithm, and you've probably seen it before. If we know that y is equal to a to the power of x, we can define that the logarithm of base a of y is equal to x. What on earth does that mean? The logarithm with a base of some number and an input of some number, it tells us to get that input, we'd have to put the base a to the power of what number. So in order to get y, we need to put a to some power x. Let's have a bit of a closer look at that graph. The red, once again, is e to the x. So that's just a constant that we'll have a look at in a second, to the power of x, and that's just another exponential function. The logarithm, the inverse of that, what value do we have to put e to get x, is the green line. And you can see, if I were to visualize a diagonal line going from the bottom left corner to the top right corner, you could see they pretty much would symmetrically reflect each other. And they do. These are what are called inverse functions. So the log basically undoes the exponential, and the exponential undoes the log. Logarithms also have a general form. Y is equal to a times the logarithm with a base of k of b lots of x take c all plus d. Keep in mind, these letters do not correlate to the ones we looked at when we did the exponential general form. But in this case, a and b still vertically and horizontally dilate the function, and c and d still horizontally and vertically translate the function. What I'm trying to say here is that exponentials and logs represent the same thing, and logarithm as a word actually means exponential. They're the same word. Power, exponential, and logarithm mean the same thing. So when y is equal to a lots of x in exponential form, we're solving for y. But when log with a base of a to find y is equal to x, in logarithmic form, we're actually solving for x. So it depends on what you want to find. They solve the same equation. Let's quickly touch on that e that we talked about before. E is equal to approximately 2.72, going only 3 significant figures. And this is called the natural exponential, or Euler's number, and that's why it starts with an E, even though it sounds like it starts with an O, Euler. But that's because it's spelt Euler, and he was German, so it's not pronounced Euler, it's pronounced Euler. And if we have a logarithm with a base of E, you can shorten it to ln instead of log base E. And it's just asking, e to what power makes y? So e is an irrational number. It's a bit like pi. It's probably going to be the second constant that you'll learn. It's used in finance, and it honestly comes up in the weirdest of places. Let's have a quick look at some key properties of logarithms. And these are useful for mathematical manipulation. When you have something that you can't solve, you can turn the problem into something you can solve. If I have a log of a, and I add it to a log of b, so the same base log, it's also equal to a single log of a times b. If I have log of a and I take log of b, it's equal to log of a divided by b. If I have a log of a to the power of b, I can take that b out of the logarithm and multiply it by just the log of a. And if I have a log with a base of c for d, then it is also equal to a log of a different base of d over the log of that same base of c. And finally, if I have log with a base of c for d, then it is equal to 1 over log of a base d for c. Here's a few additional properties. Log with a base of a for a is just equal to 1, which makes sense. To get a, I'd have to put a to the power of 1, just one lot of a. A to the power of log with a base of a, x is equal to x. And I know if x is equal to y, then a to the power of x is equal to a to the power of y. X to the power of a is also equal to y to the power of a. A final thing, if you ever see it written, usually seeing just log indicates it's log with a base of 10, and they use that a lot in engineering. And if you see ln, once again, it means for a base of e, which again rounded 2.72, and that's more used in theoretical maths.